Today we will be investigating the design of a dual-band antenna for use in a continuous monitoring sensor node communicating with a central data collecting node using the IEEE 802.15.6 standard. Before we begin the actual discussion on the design of the antenna, we will now focus on body area networks and in particular wireless body area networks. A wireless body area network is a network of miniaturized body sensor units, that is, wearable or implantable computing devices communicating with a single body central unit. Wireless body area networks support a wide range of military, environmental, home, commercial, and healthcare applications. Our antenna design will be specific to the healthcare application. We will now focus on intra-body communication as a wireless technology for wireless body area networks. Intra-body communication is a wireless technology that uses the human body as the transmission medium for electrical signals. Intra-body communication was chosen among the others as the wireless technology since it has a transmission power below 1 milliwatt and data rates above 64 kilobit per second, which is essential for implantable antennas as specified by the Medical Implant Communication Service. The two main types of intra-body communication are capacitive and galvanic coupling. For this project, galvanic coupling was used. The implantable antenna plays a key role in obtaining a robust communication link with the body central unit using intra-body communication in the presence of a hostile environment such as the human body. As the antenna has to be implanted in the human body, there are numerous requirements which need to be taken into consideration when designing the antenna. These include the antenna being very small to reduce implant volume. Also, since the antenna is going to be implanted in the human body, it must be biocompatible. This will avoid adverse tissue reaction, thereby preserving the patient's safety and preventing rejection of the implant. In order to extend the lifetime of the implanted device, the power consumption must be minimized. Lastly, and most importantly, the performance of the antenna must not degrade in the presence of the human body, as well as in the presence of the power supply and existing circuitry.
At this point, we will begin looking at the antenna design procedure. The first task in the design of the implantable antenna is designing the antenna in free space, that is, in the absence of a dielectric material and the human body. For implantable antenna design, 4 different topologies were investigated, namely the spherical, spiral, meander, and multi-layer topology. These topologies can be seen here. Based on an extensive study of the indicated topologies from previous research papers, the most efficient antenna structure was chosen for the design. The performance of the 4 topologies were reported on in the table. The spherical topology has the lowest directivity, without any remarkable efficiency. Thus, this topology was immediately eliminated, and the other 3 were considered. The spiral design has a greater radiation efficiency and directivity compared to the meander case. However, metallization of these 2 topologies reach over the region of the conformal ground plane. The very small distance between the ground plane and the metallization does not facilitate the radiation. The multi-layer topology facilitates the radiation by using the uppermost part of the volume. This aspect of the multi-layer topology, combined with the spiral conception, provides the best performing topology, both in directivity and efficiency. The multi-layer topology has the simplest realization process, and therefore this topology was selected in our implantable antenna design. The multi-layered spiral design is a pyramidal structure that is made of 4 stacked dielectric substrates. This can be seen on the image on the left. This multi-layered spiral structure for the antenna was united with a ground plane made of a rectangular planar section and a half-hollow cylinder part and can be seen on the image on the right. This was done in order to reduce the interference due to the active components, such as the battery and circuitry, on the antenna's behavior. At this stage of the design procedure, the antenna was integrated with biocompatible material. The implanted device must be surrounded by a biocompatible insulation. Human body tissues are highly conductive, and therefore the antenna would be short-circuited if the human body tissue were to make contact with the implanted device. Examples of such biocompatible encapsulation include zirconia, PEEK, and Celastic MDX4210 biomedical grade-based elastomer. We have selected the insulation to be made of PEEK because of its biocompatibility and excellent mechanical, thermal, and chemical resistance. Also, in order to extend the lifetime of the implanted device, the power consumption must be minimized. The transceiver will therefore have dual band capabilities. Such capabilities minimize power consumption as the sensor stays in sleep mode with low power consumption until a wake-up signal is sent in the ISM band, and data transmission can occur during the MICS band. Following the data transfer, the sensor returns back to sleep mode.
We now have to investigate the antenna's performance in the human body. This is investigated by building the geometry of the proposed antenna as well as the surrounding geometry, which in this case is the human limb in CAD-FICO. After meshing the two geometries, the FICO solver was used to obtain key performance results. We have based the geometry of the human limb on a simple homogeneous cylinder, which is shown in figure on the left, with muscle-like dielectric properties for the IBC signal distribution within a human limb, excluding the effect of most tissues, which is skin, fat, and bone. The properties of the model is shown in the table on the right. We will now be looking at how well our proposed antenna performed with the presence of the batteries and circuitry. The matching performance of the antenna with and without the presence of a battery and circuitry is shown in the figure here. This confirms the valuable antenna conception. The implantable antenna needs to communicate with the body central unit, which in our case is the patient's cell phone. Therefore, the implantable antenna should provide a strong enough signal to be picked up by the cell phone, but not so strong as to negatively affect the patient's safety. 3D gain plots are reported in the figure. It can be seen that the maximum gain values are taking the human body into account, negative 28.8 and negative 18.5 decibel at the MICS and ISM bands respectively. This fulfills the requirement for providing a robust communication link with the patient's cell phone, but not affecting the patient's safety. In order to ensure the patient's safety, the maximum allowable power incident on the implantable antenna must be limited. The power incident on the antenna is measured using a specific absorption rate. The IEEE standard limits the SAR average over any 1 gram of tissue to less than 1.6 watts per kilogram. Our proposed antenna was excited by a spectrum analyzer at a resonant frequency of 407 MHz located inside a flat body model. The value obtained with a 1 watt input per hour is 289 watts per kilogram, meeting the limit set by the IEEE, thus complying with the safety requirements. So far, the proposed antenna design in the simple homogeneous cylinder model with muscle-like dielectric properties performs satisfactorily. The performance in two new cylindrical human body models will now be investigated. The first was a homogeneous composition head model, and the second was a multi-layered structure made of muscle, fat, and skin. The figure illustrates the S11 characteristics of the proposed antenna in various body models in the ISM band. The S11 characteristics of the proposed antenna are nearly identical, thus showing the robustness of the proposed design versus various surrounding environments, as well as the suitability of the chosen cylindrical model initially used. In conclusion, the design for an implantable antenna for use in a continuous monitoring sensor node communicating with a central data collecting node using IEEE 802.15.6 was discussed. Physical constraints and EM requirements were discussed in order to set goals for a successful design. The antenna has a multi-layer topology as well as dual band capability. Lastly, the performance of the proposed antenna was investigated in the presence of the human body, and the results from this investigation showed the robustness of the proposed design.